So today on the bench we have an unusual instrument for me. It's not HP, it's a Stanford Research Systems SR510 lock-in amplifier. And to help us with it we have Devin, which I think is your first appearance on the channel. Right?
I believe so, yeah.
But no, long-time friend.
Friend of test equipment.
Yes, and we exchange all test equipment. But it turns out, by pure coincidence, you recently took a job at Stanford Research.
Pure coincidence.
And we were talking the other day about that. I said, okay, well, you know, I have one of their instruments to work on. Can you help out? And I said, sure.
No.
But this one is an antique, which I understand is still made.
It is still being produced.
It's incredible.
I have been calibrating these as much as a couple months ago.
Wow.
We've seen a couple integrated circuits in here that have date codes that would indicate 1991. A lot of them say 1985.
Oh, okay. So it might be one of the original instruments because it was from that time frame.
Yeah, when it was first being produced was in the mid-80s.
Hello and welcome back. I thought I'd start the elevator music early in this episode, as some of you might not be familiar with this unusual piece of equipment. A lock-in amplifier is a little miracle machine that can pull the signal out of the noise. I mean, signal literally buried in noise, as in orders of magnitude below the noise. Modern instruments, now all digital, are somewhat pricey, so the best way to get one on the cheap is to acquire a vintage broken one. Ours proudly says PLL Flaky engraved on the top. Oh yes, my kind of instrument. The SR510 is an oldie but goodie though, good enough that it is still produced today. And it uses plain old analog circuitry. I can already sense that we're going to learn a trick or two. But back to the principle of lock-in amplifiers. How do they accomplish their noise suppression miracle? Well, there is a catch. It can only pull signal out of the noise if the signal is AC and if it is at a specific frequency that is synchronous with a known reference signal. But this is a situation that happens frequently in probe response experiments. The best known example of that is probably optical spectroscopy. In an absorption spectrophotometer, for example, the probe is light and the response is how much light of a certain wavelength passes through a sample. We repaired a glorious example of such an instrument in the previous episode. However, it did not use lock-in detection. In order to upgrade its sensitivity with a lock-in amplifier, we need to add a slotted spinning wheel to chop the light. Something like this, just a disc spun by a DC motor. The detected signal will now be AC, coming on and off at the frequency of the chopping wheel. To provide the synchronous reference needed by the lock-in amp, we simply use a small optical position sensor on the wheel. We can now move our detector to the output of the lock-in amp and voila! We've probably improved the sensitivity of our instrument by a factor of 100 or 1000. Now let me reveal what happens inside the lock-in amp. The AC signal is amplified and the reference is passed along. Both are multiplied together by an analog multiplier. The multiplication result is then filtered with a very slow low-pass filter, isolating the DC portion of the product. The near DC result is then amplified once again and finally sent to the output. The multiplication and filtering has quite a profound effect. Everything that matches the frequency of the reference contributes to the DC output, as it's all flipped up to positive at the output of the multiplier and averaged by the low-pass filter. It's very much like a full bridge rectifier at that frequency. But anything that's random noise or all signals at other frequencies than the reference, even if just slightly off, will not be flipped up in perfect sync and will average out to zero after the low-pass filter. So noise and spurious signals will be eliminated. So far I described it in the time domain to give you an intuitive understanding of how it works. But if you formally work out the math and switch to the frequency domain using Fourier transforms, this is mathematically equivalent to spectral filtering at the reference frequency. Moreover, the width of the filtering is controlled by how tight the low-pass filter is. By using a low-pass filter with giant time constants, on the order of several seconds, you can reduce the filtering bandwidth to an arbitrarily small fraction of a hertz. In fact, our instrument can go down to a filtering bandwidth of 0.0025 Hz. We've just made a complicated but extraordinarily narrow filter with an incredibly high quality factor Q. And of course, the narrower the bandwidth, the lesser the noise in that bandwidth, without affecting our signal, which is always guaranteed to be in the middle of the filter. And voila, that's how our signal gets pulled out of the noise. Very clever. Now, back to reviving our second-hand instrument of dubious provenance. The major step in adjusting it is to balance the analog multiplier, so the output is as close to zero when there is no signal in. And that's when my friend Devin already ran into trouble. It shows sign of life, and then we try to adjust it, and then we discover it has a problem.
It's not as clean as it should be.
Right, so right now it has no signal, and you can see the meter is just not stable. By the way, lock-in amplifiers, I'll probably insert some elevator music, but it's made to pull signals out of the noise.
That's the end result. And how it does it is pretty complicated with some phase locking, and essentially it's several instruments all bolted together.
Right.
An RMS voltmeter, a phase lock loop, several filters in order to make sure you have a clean signal.
Right. Oh no, Devin let the cat out of the bag. The actual instrument is more complicated than what I just described. Some astute viewers who were doing the Fourier transforms in their heads have probably spotted the issue with using a square wave reference in the multiplier. If you have a component in your signal at an odd multiple of the reference, it will not cancel out perfectly. So stuff at just 3F, 5F, 7F, etc. will partially make it through. This is because the square reference contains other harmonics at say 3F, 5F and 7F. So in the better instruments, which this one certainly is, the reference is substituted with a pure sine wave of the same frequency, which does not have harmonics. It is derived using a PLL cleanup circuit. And that's the one that's apparently flaky here. Here is the real instrument block diagram. It has additional niceties such as a 60 Hz line filter and other pre-filters in the AC preamp to reject some noise up front in a classical way. The PLL also has a phase shifting feature, so you can measure the phase of the signal too if the experiment were to affect it. And the whole shebang is under microprocessor control. But other than that, that's pretty much it. In order to work, the signal has to be at a specific known frequency, which you also input into the instrument as a reference.
Right here. Yeah.
And it will look at any of that frequency in the measurement signal. So we wanted to use it for an optical spectrophotometer, for example. But it don't work, and we think we have a problem in the PLL.
When we were trying to do the adjustments for the multiplier, it says to not let a signal in, watch the output of what would be coming out, which should be nothing, but in fact gives you a look at the multiplier's noise. And this is a little more choppy than it should be.
It's unstable, but it's a reflection. We're looking at the it's a reflection of what we see on the needles. So it should be at zero completely. It's a super sensitive instrument, by the way. It goes into the nanovolts. This is where your signal comes. Right now it's nothing. This is where the reference is. That's the chopping frequency. And before it goes in the rest of the instrument, it's cleaned up by a PLL. Quite an elaborate one. Do you have the PLL signal again?
We have the PLL here, currently set at 500 Hertz.
Let me see, hold on, let me see if I can get it. It should be perfectly stable, right?
Yeah, that should be perfectly stable.
And then if I change that, it's going to change range. Oh, yeah, thank you.
So if we get all the way down such that the electronic switches in the circuit
So it's
Switch.
3, so we're, oh, there we go.
That's the one.
There we go.
Yeah. So now, very stable.
So it has to, it's fine. Actually, it's not that fine. If I look at the output, it still has a hint.
Just that. You can see some fuzz on it.
Yeah, I can see it over here.
Yeah.
So now we have to debug the PLL that we don't know how it works and it's complicated. So from what I understand, the signal comes in here, is amplified, then it goes into a first PLL, and then if I understand it correct, the output of this PLL goes into a second PLL. You thought you were done with the elevator music, but now I have to drag you into the PLL explanation. PLL stands for phase locked loop, and it is used here to create a sine wave at the exact same frequency and phase as our reference input. Modern PLLs were specifically developed for space communications, so we have already wrestled with them in our Apollo communications setup, but let me give you a refresher. The PLL input is our reference signal at frequency Fn. The PLL output should be a sine wave provided by a voltage control oscillator or VCO at frequency Fout. You can control the output frequency using a voltage applied to the VCO control pin, hence the name voltage control oscillator. The goal, of course, is to apply the correct control voltage, so Fout equals Fn and we have the correct copy. For that, we compare the input and output signals with a phase detector circuit. This circuit usually gives some pulses, which width is proportional to the phase difference between Fin and Fout. But what we really want is a DC voltage to control the VCO, so for that we use a loop filter, which will average the pulses to a near DC signal, proportional to the phase error between the input and the output. If we now connect the two to close the loop, the phase error will control the VCO until the phase error becomes 0, at which point the PLL is locked and Fout equals Fin. We have replaced our arbitrary waveform input with a clean sine wave of the same frequency. PLLs are great, but stable ones are notoriously difficult to design and even more difficult to debug. And oh joy, we don't just have one, but two in series. And they are apparently flaky. So in we go. So it's cleaning up twice. Right now we are hooked up over here. It uses a phase detector from a 4046, which is, I've made videos on that circuit, so the PL I use in the Apollo setup. It doesn't use the VCO, it just uses the phase detector. And then they have their own complicated VCO, which I think is around here. And then they have their own complicated loop filter. I think the loop comes around here. Yeah, the loop comes back here. This is the first VCO frequency, and then it comes back and it's cleaned up by a second VCO.
And then that finally heads off to give a nice pure sine wave and a chopper control.
Yeah, so this is a triangle wave VCO, and maybe this is a different one? Alright, in the rat hole we go, diving into the reference PLL schematics. It looks a bit intimidating, but hopefully it will soon make sense. Our reference input, which can be of any odd shape, first goes into a waveform shaping circuit, consisting of two stages of amplification and a comparator. The strong amplification and the comparator should transform any input waveform into a nice square wave. This is then forwarded to the input of the first VCO. There is also a one-shot circuit that indicates the presence of said reference square wave. We should check if that works, because it shorts the output of the PLL phase detector if there is no signal, and would prevent it from working properly. So we start testing the PLL, and right now we're just seeing if it goes to the first stage of amplification. So there is sine in, 3 amplification stages, it goes out here, it should be squared up, and then there's also one that so one shot and figures out if the signal is present. And it looks like this is what we have, right? Yellow is the input, right, on the BNC, right at the bottom. And green is what we get out of the amplifier chain, so it's correct. And the blue is at 5 volts, so that's the one that says we have some signal. So if you take the signal off, you should see the blue
Initially up.
come down.
And then down.
It does. Okay. So that first part's good. Alright, so now we need to go in here and look at this. Alright, the input part seems to work. Let's move on to the PLL circuitry proper. Predictably, we find a phase detector at the entrance of the first PLL. This one is implemented with part of a classic 4046 PLL circuit. This circuit, which we have already used twice in our Apollo receive circuits, contains all the elements required to make a PLL. Here, however, the designers decided to only use the phase detector portion of the circuit, ignoring the rest, which they re-implemented on their own outside of it. Assuming our PLL is locked and phase error is near 0, the output of the detector should consist of tiny corrections. So we'd expect to see tiny up and down pulses at this point. We then find an elaborate loop filter, which should integrate the phase detector pulses into a nice control voltage for the VCO. A custom VCO comes next, looking quite complicated. But I soon realized that it was described in the application notes of the IC they used to build it, the LM13600. The 13600 is another oldie but goodie. It is a transconductance amplifier, recognizable by the 2 circles at the end of the amp. Despite its scary name, it is very much the same as an op-amp, except that instead of amplifying a small voltage into a larger one, it amplifies a small voltage into a current. Hence, the amplification factor is measured by its transconductance in mhos, the inverse of ohms, instead of the familiar unitless voltage gain. Nevertheless, the very unique feature of this amp is that the transconductance is variable and can be controlled linearly over several orders of magnitude using the bias pin input. That's the input shown in between the 2 circles. This property can be used to make some of the wildest voltage control analog circuits. One of the most famous examples is the filter used in the Korg MS-20 synthesizer, a 1970s analog synth, so good that it is still made today. It's also the filter used by Luke Mom the computer in his modular synth, if you ever want to hear what this wild beast sounds like. But the LM13600 can also be used to make triangle wave VCOs, and I found the schematic used here in the datasheet. We should therefore find a nice triangle wave at this point here, which is then further forwarded to 2 comparators. The first comparator is a fixed point comparator. That will produce a square wave, which is then fed back to the phase detector to complete the PLL loop. The second phase comparator is nearly identical, except that the comparison point is variable this time, using a voltage control by the microprocessor. That will also produce a square wave, but with an adjustable phase shift depending on the comparison point. The resulting phase shifted square wave is then forwarded to the second PLL. The second PLL is essentially identical to the first one, except that it is followed by a sine converter. We finally get our phase shifted sine, which will go into the multiplier. So now that we have a good understanding of the PLL, let's do a few checks and see if we can find where things go wrong. Yeah. So they have the phase detector and they have implemented this optimized VCO over here. Why don't you put blue on that one, because that's we're going to keep that one for a long while, or green on that one, I don't know, one of the two, and the other one we're going to move around. Alright, so Devin has moved the probe, so now we are on the output of the VCO, basically is the blue, right? And we want to see what happens there. Do you see? Yeah, I see the blue unstable. Yeah. Do you see it?
Yeah.
Yeah. Oh, that's our problem.
That's what we're hunting.
So the VCO is not happy. So it should basically reproduce this and be perfectly stable, and it's not. Okay, so we have PLL trouble. Oh, by the way, we're not the first one to find out, because if you look at here, yeah, it says flaky PLL. I think we have confirmed that this is a flaky PLL. So now, what could cause PLL flakiness? So the VCO is those two. I looked that up actually. It's a classic circuit that is in the app note. So it's made with two, what do you call these again? Transconductance amplifier. So it's an amplifier where you can just change the current gain with that resistor. The complication is, so they made it really broadband.
Yeah.
So that's why they couldn't use the one in the circuit. So they used two different caps. There's some switching. Here's the loop filter, and the loop filter also has
its own control.
Its own control, so it keeps proportional to the range. So over this whole range, so that's why they control this. So the problem now, it's a loop. So it starts here, it goes back in a loop. So let's see if there's something obvious in the loop, and I think we won't see anything. We won't see that the whole thing is unstable. But let's look at the air signal. Do you want to move the yellow to the air signal? Because the yellow, we know, is in sync with our input, the green. So after a lot of debate, we have agreed to put the red on the air signal. Pin 13, U306.
Alright, we're there.
Okay.
Let's see what happens.
Alright. What? Wait, whoa. Oh, you can see some VCO operation, right? Okay, so you should see, it's digital, so you should see a little glitchy. We see it. So here's our air signal in red. It's bipolar, but that's normal. That's the way it's the output is bipolar, right? There's one transistor that pulls it up, one transistor that pulls it down, so that's normal. And it's generating an error. The problem is I don't know if the error causes the VCO to move, or if the VCO moves and therefore the error goes out. You can't tell which is the cause, which is the effect, right? And we just don't know if we have an error that's jittery and then the VCO is jittery, or the VCO is jittery and therefore the error tries to compensate for it.
It's all in a loop, yeah.
Let's look at the VCO signal, see if that gets jitter. So maybe you want to put the, okay, well, we'll debate which color to put on there. The yellow is now the control voltage for the VCO. Okay, so let's see what that happens. And I want to see if it's glitchy, and it's not glitchy.
If you zoom in far enough, barely something here.
Yeah, but that can, it should, and then it comes back to normal, so that can't explain, the VCO shouldn't have any time to change from a fraction of a period in that.
Yeah.
So 500 is here, then I go, and it's very jittery, 400, 300, it has switched to low, I suppose, right? And you see that now it uses a different VCO capacitor. I had to go to a completely different voltage, but now it's stable. So my guess would be one of the switches is unstable.
Yeah.
It's one of the range switches unstable, or the capacitor is bad. But there are so many range switches, because it's switched in here, then the filter is switched here, and then there's another switch for the output. So it could be that any of those three is introducing some noise. Of course, we've looked at the supply voltages, and those are fine, right? There's no glitch there. What do we do now? So usually when you have this thing and it's a loop and it's unstable, you need to break the loop somewhere. So and I was leaning towards breaking the loop here, and then injecting a VCO signal that we from a power supply. So this is becoming more difficult. We have an unstable loop with a subtle problem, so we can't tell where the problem originates in the loop. My usual next move in the situation is to break the loop somewhere. Here I propose to break it just by disconnecting the VCO from the loop filter by removing U308. That will give us access to the VCO control pin. We'll then manually control the VCO with an external DC voltage and hopefully see if the VCO output is stable or if the VCO itself is the source of the jitters. One additional difficulty is that we don't know what controls the high and low ranges. This is done by switching caps and other settings, and it looks like the processor is doing that. But what does trigger the change? It seems like the only thing that the processor is looking at is frequency.
The processor probably knows because one of the signals that comes out of this circuitry is the count,
Okay.
which heads off to the microprocessor.
Counter, but it doesn't know the VCO voltage.
It doesn't know the voltage, no.
So maybe it just counts.
Yeah.
And it knows it has to switch range.
Presume. If we break the loop right there and send in a specific VCO control voltage, maybe we can get the microprocessor to attempt to switch and catch that on a voltage.
That will prove that this is what's happening, right? Okay, so Devin, you have opened loop.
There.
So that's where the circuit is not. And then you have wired an input.
That's this 10-turn pot over here to pick anywhere between plus 15 and minus 15.
Yeah, we figured out that on this extra connector it was plus minus 15 and VCO. So it's for an expansion board, you tell me?
It's for a dual lock-in amplifier. Stack up a whole nother lock-in amplifier, you get two.
My dream instrument. Okay. All right, so let's instrument this one and see what happens.
Moments later.
Okay, so right now we are at minus 14 control. We have a very low input of the PLL. And that's we are not phase locked anymore because we opened the loop. So raise the voltage and it should go faster. There we go. So now you're what? It's written very small here. Oh, it still doesn't have enough edges. 83 Hertz. Okay, and the error is doing fine. So far so good. The VCO is responding. And then we want to go up to to 500 Hertz. And we're going up to 3 volts and boom! It has switched here. So now it's in high range, so this is what we thought. It's the counter that switched it. And now we need to go down.
Yep.
You're still at 4K, 1K. Okay, so now we're getting back to where are we?
Getting close, but
okay.
Every little.
So the problem is, it's stable first, it's working. But I see what the problem is that to be at 500 Hertz, you have to be at minus 14.4.
Yes.
It should have switched way before that. If you try to get to 500, it will switch on you, right? Or try to get it a little lower. What is that? 400.
That's about where the switchover point was.
400 Hertz.
And now we're at 400 Hertz. It still hasn't switched.
There
we go.
There you go.
So somewhere south of 400 Hertz.
So the main result is that the experiment was successful. After breaking the loop, the VCO is stable after all. So my next conspiracy theory, I'm starting to run out of them, is that we are sitting at the boundary between high and low range, and the VCO control voltage is hitting the negative rail, so the loop cannot control it properly anymore. That would also explain why things stabilize once we force it to switch to the low range, where the control voltage returns to the middle and the loop regains control. Maybe, perhaps, we don't really know how this is supposed to work when it's not broken. What would really help is another instrument for comparison. And as luck would have it, we can check with you brought a good instrument. I think we should do that, right? since we have the luxury of having another instrument, why don't we
Take a look at it.
check that one and see if we are interpreting this correctly. Alright, Devin, you've put yours and our theory that our VCO was adjusted wrong is fails. It's also at minus 14.5.
Yeah.
400, 300, it switches. And it's going to be minus 3 volts, and I guess it's, if I get it, it will go up to...
Go down to minus 14. Just about the same ranges, yeah.
So this is not that. And then we observe it's also slightly jittery at 500 for the same reason.
It's definitely at an extreme end of its range. 500 hertz seems as the very, very bottom end of that range.
I'm tempted to give it a little bit more capacitance so it doesn't have to go that far down before it switches, and see if that makes things better. Yeah, put 500 puff on it. Right? Yeah. Devin has added a little extra cap, and we'll see if that stabilizes things. And so we have more of our theory that takes water here. We increase the cap now to
twice, doubled it.
with all of it. We added 0.01 micro, and we barely went up in voltage. Now it's at 14.3 instead of minus 14.5. It moves a little bit away from the rail, but not as much as I thought. So at this point, desperation is starting to creep in. None of the mods that we made, breaking the loop, doubling the capacitance, helped at all, not even a little. Even comparing to a good instrument led to very little additional insight. So we close back the loop by putting back the IC and resume our head scratching. Okay, so we're back. We put the circuit back in, so we're back into PL mode closed loop, and my unit is still very jittery. It's way more jittery than yours, I think. And that still was the extra capacitance on the VCO. That hasn't done squat. Okay, so now we have damning evidence that my unit is not PLLing correctly. My unit is the blue, and Devin's unit is the yellow. And mine is moving all over the place, and he's moving a little bit, but not as much at all. Things were looking pretty dim. We had tested a lot of things which confirmed our correct understanding of the basics, but did not have much to show for our effort. However, since we don't give up easily, we continued poking at the device. And that's when we had a revelation. Well, you want to go over a revelation here that we think is a measurement induced instability that affects my unit but not yours. We're measuring both on the red here, the triangle, and on the blue here, the square version of it. And now if we turn my unit off and remove the red probe, that works. When we don't measure it, it's a quantum thing. Now my unit is stable, as stable as your unit. So it was a measurement induced instability that affected my unit but not yours. We're measuring it where? Here. Ah, yeah, 10k impedance. It's buffered. I wouldn't have expected that, but that's what it is. And apparently, it's right on the edge because yours was very, very slightly unstable, but
Very slightly,
but not as affected as much as mine. Yeah. So the PL is working fine. Thank you very much. Okay, so all this tempest in a cup of tea, all this for nothing. It's fine. Not jittery anymore. Should we remove our cap and make sure it stays like that, even with the cap removed?
Yeah, we should. Alright.
And
All done?
okay, mod removed, and alright. We're back into the original configuration, and now we'll probe it the way that doesn't bother it, and see if it's stable again. Okay, well, we repair our units by not measuring it. So we're chasing our tails. I hate when that happens. Well, that's very annoying and embarrassing. Our problem was induced by our own measurements, but I still wanted to post the video, as it wouldn't be the first time that we have had a Schrödinger cat problem. I'm pretty sure it has happened to some of you too. However, going back to the beginning of the mad chase, why was our instrument noisy when we tried to calibrate it? Did we do something wrong there too? So Devin went right back to doing the calibration procedure, now comparing the two instruments.
The measurement that's being done right now is the signal has absolutely nothing going into it. This is terminated. That's what's being picked. There's no filtering. So the only thing that could be coming from the output is any sort of noise coming from this set of PLLs as it goes through this multiplier right here and chops up the signal.
It's detecting it.
And so that detection right now, even at the settings that the manual says it should be, 2 volts in 5 milliseconds, really small.
Okay, and on my unit?
Your unit.
You've put a termination. Yeah, I know. I have to buy the expensive ones.
We're seeing much the same.
Yeah? And mine is even better than yours. Because you just aligned it?
Probably. If we go down...
So is my unit fine?
So this was the sort of flopping around that I was seeing. But that was at higher sensitivity than the manual says that this should be done at. If I were to pull mine down to the same sort of level, then it's probably going to be, not much better.
It's worse.
Yeah,
Because yours, no, similar.
Somewhat similar.
Right. It still has a little bit of the 30 Hz or 50 Hz or whatever it's supposed to be. So you just recalibrated my instrument, so it's perfect.
Yeah.
So Devin had calibrated my instrument perfectly. We were led astray by choosing too high a sensitivity during calibration, on top of being biased by the flaky PLL marking on the chassis. Mind you, I am not complaining about it. I learned a ton about the machine and will feel quite confident to repair it if something goes wrong in the future. Anyhow, let's celebrate our dubious victory by trying to measure some minuscule signal with it. Okay, so we put a signal and a million attenuators and see if we can pull it out of the noise.
Yeah.
Okay, so now we're going to try to lock a signal on both. So we have a whole bunch of attenuators here to make a really small signal. Right now it's off. I'm going to turn it on. And they both seem to give the same result, I would say.
Pretty close. A little bit. Very, very slight difference, but very close.
Okay, that's as low as I can go.
Well, this one's having a bit of difficulty, so I'm going to put him down another range. Yeah, they're really flopping around.
They're about the same level of noise. So we're now in tens of nanovolts.
At this point, we should turn up the time constant.
Yeah, time constant. Yeah, time constant is too. At 500 Hertz is too low. Yeah. But okay, so we're measuring what? Is that the lowest range it goes to?
In the nanovolts range, yeah.
Yeah.
Yeah, 50, roughly around 50 nanovolts.
Okay.
Pretty low.
Can I invert the phase? Haha. Let me see if I'm phase sensitive. Phase. Phase.
Adjust it, add it, and give it 90.
Phase 9. Well, 90 is going to give me 0.
Exactly, yeah. And then we can adjust the phase over here and bring it back.
No, I want to see if it goes negative. I'm going to go 180 degrees.
Okay. It's off the other way, yep.
It's good, so it's measuring our signal.
Yeah.
Okay, and then now we are going to do a quadrature signal at 90 degrees.
All right.
And now it should go to Oh yeah, but that guy is never... it's an annoying thing. Ah man, this is an annoyance for my modern Keysight dual channel generator. Unless you press sync phase, the two channels are not calibrated in phase at all. So I'll try that.
Yep.
Okay.
Yep.
Alright, so now I'm at 90 degrees. Can you recover it by setting the thing to 90 degrees?
We can increase phase on here.
Do you have a 90 degree button? Yeah, there you go.
And then they're back.
So we can measure phase too. Alright, well I think our unit was just fine all along. All you did is a fine tuning by the master and the pupil not to be so worried.
Oh, this was the apprenticeship, was this whole operation.
Well, thank you, master of phase lock loop. Well, not phase lock loop, lock-in amplifiers.
Fine equipment.
Yeah. After Devin was gone, I tried my lock-in amp on a small absorption spectrometer setup that I quickly cobbled together out of mismatched parts. But it has all the basics: a light source, a chopper disc and its attendant controller, a few narrow color filters, and a silicon photodetector which you can simply plug into the lock-in amp. Noise is going to be ambient light, as I made no effort to shield anything, which you would not do in reality. And guess what? It works as advertised. You would have your sample that you measure over here, and it would go into the detector. And now it's measuring a lot of light, but the light is not modulated, so the lock-in sees nothing. It's at 0. However, if I now put my detector in here, it should show up pretty soon if I aligned it properly. Yeah, there you go. It went out of overload. So now I have some signal. There's way more ambient light than there is signal light. But the ambient light is invisible to the lock-in amplifier, and that's why it's able to pick up the signal. And the sensitivity is quite ridiculous. I can turn the light down quite a bit. There you go. If I go here, it's fine. So that's what lock-in amplifiers do. If you're not in a hurry, this is a very slow instrument. You can pick up signal out of all kind of noise by just listening to its modulation frequency. So here goes Stanford Research Systems SR510 lock-in amplifier.